As mankind turns their eyes to the moon once more, robotic explorers are needed to pave the way for future manned missions. With a new breed of miniaturized rovers under development for this explicit purpose, similarly miniaturized scientific payloads are also required. As part of a HeroX design challenge, NASA is seeking mini payloads to make lunar exploration more effective. My entry to this challenge are deployable micropayloads for localized radiation surveying. This proposed payload would consist of a series of smaller self-contained micropayloads that would be deployed from the rover to conduct long-term radiation measurements of a specific location on the lunar surface. Each self-contained micropayload would be solar-powered to maintain basic internal power systems and be equipped with an RTC and solid-state internal memory for logging and storing data collected from an ionization radiation detection chamber. A short-range RF communications system would be utilized by the micropayloads to communicate data back to the base station on the rover from which the micropayload was released. To demonstrate the feasibility of my design, I have created a simple benchtop prototype that will be demonstrated in this video. The housing and internal mechanics of this prototype were created using a common CAD software and then 3D printed for field testing. Notably, the majority of this prototype was non-functional, but it was designed to show that all of the general elements of my proposal would fit within the designated payload envelope. It is pertinent to note that I have bench-tested most of the functional elements of this prototype using commercially available electronics, but for simplicity's sake, I did not attempt to integrate all of these independent systems for this prototype. Beginning with the micro payload, this device would contain the pertinent sensors to be deployed on the lunar surface, and would represent a completely self-contained system. For this proposal, the benchtop prototype micro payload was equipped with a simple ionization chamber, which utilizes technology that has been employed in radiation surveying equipment for over half a century. This prototype was created in a series of layers that contain all of the pertinent electronics. The first layer, to be fitted within the 3D printed enclosure, contains a 300 mAh lithium polymer battery, micro SD card reader, voltage regulator, 315 MHz RF transmitter, and voltage sensor for the ionization chamber. The next layer to be added is one half of the ionization chamber. This conductive plate will be charged with a small voltaic potential, with the third layer containing the upper half of the ionization chamber and another charged plate. The last and topmost layer includes an RTC, Arduino Nano, and solar charging controller. The enclosure is topped off with a 500 milliwatt solar panel that would power the system once deployed. For the base station, this element was designed to fit exactly within the payload envelope specified by NASA, and its primary purpose would be to contain and protect the micro payloads until deployment. Once the micro payload is deployed, the base station would provide a means for the rover to communicate with the payload. The benchtop prototype was designed in a series of layers, with the first containing all of the pertinent electronics for this device. This includes an Arduino Nano, RTC, micro SD card reader, 315 MHz RF receiver, and a serial connector for interfacing with the rover. After a small spacer is inserted, the launch chute can follow. A 5-gram servo with a specially designed gear is also part of this launch chute. The gear interfaces with the micro payload to keep it securely within the chute until deployment. Finally, the casing cover is held in place with 4 screws. Once completed, the micro payload slides smoothly into the base station. Activating the gear system would prevent the micro payload from falling back out of the base station. To field test the payload deployment system, the benchtop prototype was mounted in an existing mobility platform. This simulated rover has 2 power drive wheels that allow it to negotiate moderately difficult terrain. In addition to being completely wirelessly controllable, the onboard microcontroller on the rover was also interfaced with the payload launching system on the prototype payload for this field test. This allowed the geared release system in the base station of the prototype payload to be operated remotely and without any physical human interference. With construction of the payload complete, the micro payload may be properly loaded into the base station. Extrusions on the outer housing of the micropayload were designed to interface with the servo-turn gear within the launch chute of the base station. This single-geared motor of the servo is more than adequate to draw the micropayload securely into the enclosure, but the process can just as easily be reversed to release the payload. Moreover, during field testing, the system proved to be successful in securing the micropayload on the rover, even while the mobility platform negotiated rough terrain. Then, when the command was issued to release the payload, the micropayload was easily dropped from the bottom of the rover. This design would be particularly effective because once the rover had paused to drop the package, it would then be free to continue to explore and carry out science objectives without the need to wait for the payload to conduct measurements. Also, while only a single micropayload was able to be fit within the base station for this field test, it is possible that further miniaturization of later designs may allow multiple micropayloads to be deployed from a single base station. This would provide a unique opportunity to conduct radiation surveys from multiple locations on the lunar surface. Thank you for your time and consideration of my proposal. I look forward to possibly playing a part in returning to the moon.